You for the great introduction. I'm very happy to be doing this virtual training today from our live fire lab at Eat Energy. As was identified, my name is Michael. I'm sure that some of you that are on this chat, I probably know who you are. My role is I am the general manager at Eat Energy Equipment. I am also the technical trainer. I've been involved in hydronic heat pump system design, troubleshooting, and installation pretty much my entire life. I've grown up in this industry. So the point of today's sort of webinar is we're going to be about an hour, and we're going to talk about what does it mean when we talk about a phase change thermal battery. Obviously, we're not going to get into any specific brands. The point here is not to talk about a brand, but I am sitting in a live fire lab that's using phase change thermal battery, and I'd like to use that opportunity to sort of show what it does and answer any questions as we go through the PowerPoint. The QR code that you see currently on the screen is a QR code that you can use to contact me. So if you take your phone out, take your just your camera app and hold it over that, you'll see a little link pop up. You click on that, you hit save. That's me. Throughout the presentation, I do have a few spots where I put QR codes so that you can get more information about whatever topic it is that I'm talking about. And as was identified at the beginning, as I'm going through this presentation, if there's a particular question that comes up, please do ask the question. And we will be certainly well aware to answer your question as we go through this presentation. So right off the bat, I want to sort of talk about, what are phase change thermal batteries? So I can't really put my finger on when I first saw a phase change thermal battery, but phase change thermal batteries are something that have been around for a very, very long time. So phase change thermal batteries, believe it or not, go back as long as World War II. So there was rocket systems being developed in World War II that were using a variant of a phase change battery to power rockets. So obviously that was not reusable. You couldn't use it in an application like we're talking about now. But the idea behind a phase change battery is that it stores and releases energy. So that would be similar to how you would do with a lithium battery. The difference is our conversation today is we're talking about how we can use phase change thermal batteries for a hydronic application. So right off the bat, the question typically becomes, why would I want to use a phase change battery? What is the advantage of a phase change battery? And, some of the other things we're going to talk about are some of the potential disadvantages of using a phase change thermal battery. So phase change thermal batteries are new to North America, but they are not a new technology. If you look at in Europe, there are literally tens of thousands of phase change thermal batteries being installed in residential applications that we're going to talk about. There are also large-scale industrial and commercial applications for this technology. And what's really cool about phase change thermal batteries is the opportunity that it has for us in hydronics. You'll see them used in a variety of different applications, but the one that really excites me the most is the ability for us to use it in a hydronic heat pump application. So as far as, what kinds of phase change thermal batteries are out there, there's quite a few manufacturers in Europe. I've listed a few just so that you guys can go out on your own and do your own research, because the goal here, again, is not to speak to a particular brand or promote anything. So you've got a variety of different ones from Climcell and Syntef and others, and I've got some photos I'm going to share with you. And of course, Sunamp and Plentygrade. And then the other one that I've actually just included in this slide is Steffes. Steffes being a Canadian product. And again, just sort of giving the different options for what is a thermal battery. So a phase change thermal battery, we're going to talk about in a second, but I want to talk just about a thermal battery. And I'm sure many of you watching this understand what a thermal battery is. So some thermal batteries, in the case of the Steffes unit, and I have no affiliation with Steffes, is that they will use bricks to store energy, right? And I'm simplifying the concept of it, but it's basically a apparatus that fits inside of a large filing cabinet that stores energy. And so there's a lot of different ways that we can store energy, and there's a lot of advantages that come from us being able to store this energy for use in unique and creative ways. And we'll touch a little bit on that as we go through the presentation. So I touched a little bit earlier on about sort of the history of thermal batteries and the fact that it's been used in some interesting technologies over the years. Thermal batteries have been worked on since the early 1900s. Going right back to the 1915 is when some of the early thermal battery work was being done. And sort of like when we talk about condensing boilers, we can say condensing boilers go back to Milwaukee when the very first ones were made. Obviously, that condensing boiler looks nothing like what we have now, but they all have their roots in technology. And basically what happens is the original batteries used what's called calcium chromate, and it was a primary heat source. And what they were doing is they were causing a chemical reaction between the calcium and the chromate that would produce heat. And that is the whole principle of a thermal energy battery. Now, the challenge with thermal energy batteries is not every thermal energy battery is made the same. And that can be, some are lacking in technology or some are lacking in application. So what can happen is that some of the earlier thermal energy batteries had limitations in just the simple fact they couldn't store a lot of energy. And so the way that you cause a thermal battery to phase change is with heat. How you generate that heat is entirely up to you. And in the early days of thermal energy batteries, you had to produce industrial levels of heat, like you're talking 1600 degrees in order to phase change a thermal battery. So my entire discussion today is around hydronic applications for residential, and behind me is a residential hydronic heat pump setup. So as you can imagine, I don't have anything in this lab that's going to produce those kinds of temperatures. And even if I could produce those temperatures, the density of the energy was not very good. So what's really changed in the last few years is you have leading universities, whether it's Queen's University, MIT, and some others that I can't name, including ones in Europe. They've been doing research on the chemistry and how they can and work on this material to make it phase change at temperatures that are more ideal for what we have now. So what they've focused on is the manufacturers have focused on the energy density, the lifespan, and most importantly, the safety characteristics of the product. And by safety characteristics, what I mean is if you're going to put a phase change thermal battery into somebody's house, you want to make sure that if there's any problem with that, it's not going to have a negative impact on the occupants. So we want to make sure it's safe. And the good news is that for the most part, phase change thermal batteries are quite safe. Now, the traditional way for doing thermal storage, and this is how I'm doing it in my house. In my house, I have a air-to-water heat pump installed, and I'm using a large buffer tank that I'm using for thermal storage. And so the idea behind that is I will charge my thermal storage tank off peak, taking advantage of low peak rates. And I'm also storing those BTUs for when I need them later. So the advantage of that is it's quite simple. It's very affordable. Everybody on this call knows how to install a buffer tank. So the complexity is easily adoptable. We don't have to think too hard about it. The other thing is that water can absorb and release a significant amount of heat. Now, the challenge with water is we can't store sensible and latent energy. Those are two different things. And that is one of the bottlenecks of using water. The other thing with water-based storage is what we just said. Buffer tanks, it's not new technology. We don't need to explain to people how a buffer tank works. It's very easy to go in and do water storage. The challenge with doing water for thermal storage is that it does require a fair amount of water. And where I'm going with that is that because when you store with water, you have very high standby losses in comparison to a thermal energy battery, you're going to end up with the issue of you're going to store a lot of energy and you're going to lose a lot of energy. So in my own house, my water-based system, it doesn't work all that great. The way that I test and can verify how it performs is right here, and hopefully everyone can hear me okay. This is a Measurement Canada certified energy meter. And so I also have one of those in my house. And that's what allows me to collect data so I can see flow and BTUs and pressure drop. I can see a lot of different things. And what I found in my house by doing water storage as a thermal battery is the standby losses. It's not usable heat. So what I mean by that is I charge it today, and if I want to use that energy in 2 days, it can potentially end up being a problem that I may or may not have that heat available to me. The other thing is that the effective range at which the water is usable can be a challenge as well. It's okay in some applications, but the water is not always going to be the best case. And where I'm going with that is that we have to store it at a very high temperature to get usable heat out of it. And in the case of an air-to-water application, I can't produce high temperatures. So storing in a water-based buffer tank like I attempted to do in my home, does it work? Yeah. Could you take that to somebody like MIT and show off and be proud of yourself? No. So that's a limitation. And obviously the big thing is the amount of storage that is required. So we don't have a lot of space to be going into residential homes, for example. If we looked at an air-to-water application and said, listen, we'd like to use thermal energy storage. We would like to store 4 or 5 tons of capacity in the basement, usable for you at any time. Well, if we try to do that with water, you're talking a massive vessel of water. Whereas if we do it with a PCM battery, it's insignificant. The reason I wanted to be sitting here in the lab is it's better than a PowerPoint slide for you to look at. So I just want to point to is right over here. This is a thermal energy storage battery. You can see I'm sitting in a chair. It's the size of a small filing cabinet. Well, that's the equivalent to 300 gallons of water, which is not insignificant. So what you're talking about is I can actually store 4 tons of capacity, which is the capacity of that battery, and I can fit it in a very small footprint. Like I can stick that in a closet, I can stick it under a staircase. So it's typically 3.5 to 4 times smaller than typically what you would see in storage. In Europe, what you will see is they have even smaller units. I'm going to show you just so you can get perspective. In Europe, they use units that are actually this small. So literally, you're talking about a unit that is the size of a microwave, and in that case, they're putting them on a countertop. So there's a lot of creativity that's happening with PCM batteries, and there's a lot of opportunities with PCM batteries. And if you go across Europe, a lot of the different countries all have manufacturers that are scaling up and developing technology that's going to meet this demand. And the nice part is that PCM technology is a really effective way that we can go into residential homes across Canada, frankly, across anywhere in the world, and we can reduce the carbon footprint, we can reduce the gas consumption, and we can do it in such a way that anybody on this call can do it the second we're done this call. The learning curve is very limited. Might be a bit of an exaggeration, but you don't have to spend 2 weeks in training. You can spend an hour with somebody who is very capable and have a good design, and you can go out to your customers and you can start reducing their gas consumption by up to 50%. You can reduce their CO2 production by 36%. Why do I know these numbers? Because I have smart friends. There's lots of research out there that you can look to, and I'm going to speak a little bit about that as I go through the presentation. So we sort of talked about water and some of the advantages and disadvantages that it has from a phase or a thermal battery standpoint. The advantages from when it comes to a phase change thermal battery is its ability to absorb and release heat during phase change. So for those that are not familiar with phase change, we'd be referring to like water when we freeze it or when we go to steam. We need to actually change the phase in order to store the sensible and the latent energy. And so it's really interesting because with a phase change battery, you can store a lot more energy in a smaller space. The thing that has held phase change thermal batteries back is that we typically needed industrial temperatures, like very, very high temperatures to do that. Now what we're seeing is companies, pardon me, I'm recovering from a cold. You're seeing companies in Europe, whether it's in France or the Netherlands or Italy or Scotland, that are developing phase change thermal batteries that can produce usable heat at as low as 43 degrees Celsius or 120 degrees Fahrenheit. So as you think about that, I've got an air to water heat pump sitting behind me. For it to produce 120 degree water is very, very easy. I can still maintain a COP in excess of 2, which means that this technology, depending on which manufacturer is manufacturing the PCM material, we actually have usable technology right now, which is the point of this discussion, to start talking about what could we do. The other nice thing about PCMs is they come in a variety of different ways. So when you look at a PCM battery, the construction of the battery is very proprietary and specific. So it needs to be in a completely sealed canister. It has to make sure it can hold on to its moisture. There's a lot of chemical properties that go into that battery to make sure that it's going to be able to phase change back and forth between a liquid and a solid over a wide temperature range and over a wide period of time. So when you're looking at PCM batteries, you would specify for a PCM battery what battery you want. So you would get one that phase changes at 43 degrees C or around 110 degrees Fahrenheit. You could do a 55 degree, a 58 degree, or you could do much higher. So you'll see commercial applications where they will get PCM batteries that are larger than the room that I'm sitting in, and they may phase change those at 176 degrees. It really comes down to what you need. The nice part is that when you do this, you have that energy stored, and the heat loss on these PCM batteries is negligible. So again, we talk about water-based standbys. We know what the manufacturers state the water-based standbys on a buffer tank are, which is how traditionally we would do a bit of thermal storage. There's a lot of other things that come into play. Do we have check valves on it? Did we pipe it right? Did we thermally trap it? These are all things that typically don't happen, including my own house. I didn't thermally trap my buffer tank. I wanted to see what it would do. Well, by not thermally trapping my buffer tank, if I charge it to 130 degrees, I come back the next day at 70. Right? When you look at a PCM battery, you don't have those same challenges because the energy is all stored in the PCM battery, and it's only leaving the battery when you actually are flowing through that battery. So they have significantly less reduced heat loss around it. There's a lot of really cool studies that I've had the opportunity to look at that have not been published yet. But what I can say to you is that if you charge a PCM battery and you come back in a few days or a week, that PCM battery is still charged. So that's significant. The fact that we can charge the energy and store it for when we need it it's going to open up new opportunities, especially if we start looking beyond air to water heat pumps or boilers. There's a boiler in this lab as well. It also gives an opportunity for solar thermal to potentially be revisited, because solar thermal faces the same challenge of when we have the energy and want to store it is not necessarily when we want to use it, which is why solar thermal has been a bit of a challenge for adoption. But when you have a PCM battery, it starts to open up a lot more opportunities for you. So when we look at a thermal battery, so this is actually just a chart for the one that's sitting next to me. So basically what ends up happening is you can see the energy that's being stored in this unit, starting at 45 degrees C. So basically what happens is as I'm charging that battery from 45 degrees C and I get up to about 58 degrees C, all I'm doing is storing sensible energy. But because at that point I've initiated the phase change, what I'm doing then is I'm now storing all of that latent energy in the battery. So in the case of this battery that's sitting to the left of me, when this is the graph to go with that battery, it has the ability to store 48,000 BTUs, which is quite significant. That's a lot of energy that we can use for a lot of different applications. And obviously you can get larger batteries, you can get smaller batteries, you can daisy chain batteries. The key to that is this is the equivalent to you having 300 gallons of storage, but the key of it is that that energy is available to you when you actually want it. Now, as far as how these batteries get charged, there's a variety of different ways to do it. And that's why I wanted to be in the lab, just to sort of illustrate some of the ways that they get charged. And again, I'm not trying to pitch any products, but I think it's important you get to see an actual physical product. And then I encourage you, go on the internet, look around, ask questions, reach out to me. I'll put you in touch to every manufacturer I can possibly think of. I enjoy doing that. But typically what happens, and if we look at this unit here, is you can see that they'll typically have ports on the back of them. So this particular unit has 4 ports on the back. So what that means is 2 of the ports will be hooked up to an air to water, like I have right here. The other 2 ports can be used for your heating load. And I should also preface, you can get PCM batteries that are also designed for cooling. So you can do heating and cooling with a PCM battery. This cutaway is just showing the inside of the battery, but I don't want to focus on the brands. We're going to keep spinning here. And the other thing that comes into play is that a lot of them actually come with an element built inside of it. So in the case of this battery that's operational right now behind me, it has the ability with 2.8 kilowatts of electric to charge itself in just over 4 hours. So if you looked at off-peak charging, for example, you could charge it off-peak electrically. You could charge it with solar PV. You could charge it with solar thermal. You could charge it with your boiler. You could even charge it with an air to water. Lots of opportunities on how we can use this technology. Now, from a storage standpoint, we talked about the fact that it is extremely energy efficient, which is great. The fact that it's energy efficient means that we don't have to worry about the standby losses that we might have in other storage systems. I've worked with people like Stuart Evans from Zon Engineering on designing large water-based thermal storage systems. And in those scenarios, we had to be hyper focused on how we insulate and store that water, not least of which in some cases it was thousands of gallons of water. The other thing that's really interesting from a discharging standpoint is that, again, it's going to release the energy when we actually want to be using that energy. In this case, I've actually got this photo from PV Magazine. If you guys don't read PV Magazine, you should start. So this is a unit that was made in France. It's a thermal storage unit. The link is on the bottom. But again, if you scan that QR code at the beginning, shoot me an email, hook up with me on LinkedIn. I'll gladly send you these links so you can have a look at them. So there's a bunch of different options that come into play. This is one that I had the pleasure of going out and seeing, and this is a plumbing and HVAC project. So on the left-hand side is a QR code. If you scan that QR code, you can watch the entire video of me talking about this technology. And so what this was is they were using a PCM battery as storing rejection heat off of a micro CHP system. So what happens is the micro CHP in this building, I can't remember the name of the building this was in, but this micro CHP system was generating power, and the waste heat from the power was being stored in the battery. And then they were using that battery to produce the domestic hot water for the space. So the heat exchangers in these, they're very versatile in that they don't really care what the medium is. You can use them for domestic, you can use them for heating, you can use them for cooling. You just need to make sure that you pick the right PCM battery for the application. So high energy density is key here. We talked about that. Hopefully the visual representation of this one and how tiny it is helps you understand. It's a little filing cabinet versus 300 gallons of storage. The other thing that's really important is the lifespan. And obviously not every battery is made the same, whether it's a PCM battery or any other battery. I'm sure we've all had the experience of, your cell phone battery craps out, now you got to get a new cell phone. But the key thing around these PCM batteries is long life. There's a lot of manufacturers around the world that what they're focused on is the chemistry, not the container. The container is the easy part. And what they're looking at is seeing what they can do to get really long duration from the standpoint of flipping back and forth between a solid and a liquid. So there's technology on the market now where you can easily get 10 or 20 years of cycle out of this product where it can cycle back and forth easily 50,000 times. The other thing that's really unique about a thermal battery is that you have temperature stability. And so if you go back, and in fact, I'm just going to go back to my graph. When you're storing all of that latent energy, when you draw this battery down, it's not like a stratified buffer tank, for example. The entire battery is the same temperature. So what you end up having is real stability. And what ends up happening is, unlike a traditional buffer tank, your piece of equipment isn't cycling as much, right? Because it's a stable temperature until we draw off all that latent energy off of the battery. And so a lot of these batteries are designed with temperature probes that run the entire length of the inside of the battery so they can see what the temperature is. And so the other thing that's really nice in this technology, obviously, is the scalability of this. These are all designed, regardless of manufacturer, that you can get much larger boxes and put them all into parallel series with each other, or you can actually just get bigger ones, smaller ones that really, I've got pictures of projects from a variety of manufacturers from all around the world who shared this is how we do it. So there's a lot of opportunities from scalability. And the other thing that's really important is the safety factor of this. Now, obviously, refer to the manufacturers. I can't speak for any manufacturers, but typically it's salt. And those of you that are on this call and know me, it wouldn't surprise you that I've taken one of these samples apart. It's salty, so it's non-toxic, it's non-flammable, it's human safe, and similar to some of the indirects that you have out there that are reverse indirect. You're not storing any water inside of this unit, right? The entire contents of this are PCM material with a small heat exchanger inside of it, so we don't have to worry about, for domestic hot water operation, Legionnaires, for example. Now, one of the sort of thoughts that popped into my head as I was having my adventures of going around the country and talking to really interesting people is the idea of storing BTUs and not watts. So I like to think I coined the store BTUs, not watts, at least until I find out somebody else did. But the idea behind it came to me because I was at a site. I'm going to share some photos of it with you guys. And on this site, they had a PCM battery that was producing upwards of 80% of the domestic hot water. Now, when I was on this site, I was fortunate that the utility was there, and so were the people that installed the solar system. So what they ended up doing was they put a solar PV system in to charge that element is in the bottom of the unit. And that's how they were able to produce 80% of the domestic hot water. I'd say it was about a 2,000 square foot home. I believe there's 3 people living in it. And they had been collecting and logging data similar to how we do here with our Measurement Canada meters. So I could actually look at the data. Not that I don't believe them, but I want to see the data. Now, one of the really cool things that came out of that conversation is because the solar PV person was there, I had the opportunity, and there's an illustration on the right-hand side of my slide, of asking the question of how would this come into play from the standpoint of storing BTUs versus storing watts. So in this case, what we ended up doing was we were storing, as identified, about 48,000 BTUs, 47,700 to be specific, and they figured the total cost would be about 5 years. And in this case, they expected the life expectancy for the unit to be 10 years. So basically, that means it can cycle 43,000 times. For us to do the equivalent in electric storage, it would be $15,000. And the way that it was put to me by the gentleman who owns the solar PV company is that's just the battery. That's not the permits. That's not all the other things that come with it. The nice part about the PCM battery is it's 4 pipes, right? You don't need to pull any permits. There's nothing special about it. It's literally a box. You drop the box in, you pipe it, you're done. Pardon me. The other nice thing about the technologies we talked about earlier is it's agnostic to how you charge it. You can charge it with anything that you want, and the cost proposition is quite enlightening. So this is where I came up with my saying that some of you might have heard, I talk about a lot when I write or on the internet, is why don't we store BTUs and not watts? So this is a good illustration of that. It's obviously very small. You don't have to get on the roof. There's no electrical components other than obviously an electrician would wire the element if you're going to use it. And in the case that I'm talking about, that's exactly what they did. So here I just have an illustration. It's not my illustration. I've borrowed this from a manufacturer of Scotland. What this illustration is showing is just some of the ways that they've done it. So really, heat pump is what I want to talk a little bit about today. You could use a chiller, you could use solar, whether it's solar PV or solar thermal. You could do a micro CHP, which I showed you a photo of earlier. You could use waste heat. There are a lot of different ways that we can achieve what needs to happen. The one thing that I would caution you is you do need to be careful with a PCM battery. Just like any technology, know the limitations, know what the low temperature limit is, know what the high temperature limit is. As much as, you know, this is not rocket science for us to install. It definitely is rocket science to make a PCM battery. But inside of the battery itself, at least in the ones that I've had the pleasure of looking at, there are no moving parts. So there are no moving parts in this battery next to me. It's literally just a heat exchanger with PCM material and an element in the bottom. So cool technology, a lot of different ways that we can apply that. One of the things that I think is really exciting about PCM batteries, especially as we start to adopt air-to-water heat pumps on top of, not just storing BTUs, is the ability for us to balance the curve. And so what I mean by that is that you will start to see, because in Quebec, there are incentives for thermal storage, where people will start putting in thermal batteries and they'll be able to store the energy electrically to heat their home, provide domestic hot water for their home, whatever the case may be, and they can take advantage of the off-peak rates. Like in Ontario right now, we have that ultra low overnight off-peak rate. Well, my air-to-water heat pump at home, if I didn't have a thermal battery on it, and for the record, I don't, I have a water-based one, but with the water-based thermal battery, I run it off peak. I try to hold on to those BTUs, and it doesn't cover my entire heating load. I don't delude myself that way, but it allows me to at least get some energy on peak. Well, the nice part about using a PCM battery is that I charge it. That usable heat is there until I need it. So until I use that heat, it is there. So what you're going to see is you're going to see PCM battery adoption happen, in my opinion, on the commercial and industrial scale, because that's the easiest place for them to really start to balance the curve and help with some of the demand issues that we see as more heat pumps come on board. So it's going to get very interesting to see how that happens and where things go from that standpoint. So the ability for us to be able to take care of this and go off peak and take advantage of off peak rates, I think is going to be very good. The other thing that's really interesting about this is because we are reducing the consumption considerably, it also means that we're going to be able to reduce, even if we're using it in a fossil fuel application, we're going to be able to reduce our gas consumption as well as our electrical, our CO2 gas. So why do we want to integrate thermal energy storage? Well, there's definitely a couple of reasons that we would like to integrate thermal energy storage, not least of which it helps us with an energy supply if we can actually, load shift some of the people that are using heat pumps and are not using them on peak all the time, using them off peak. Obviously, it results in savings. The other nice thing about using a PCM battery is it results in, they don't have the same standby losses as we talked about, which is significant. We've talked about temperature fluctuations, which is really nice as well. The other thing that's quite cool about an air-to-water heat pump is that when we look at an off-peak rate, so in Ontario, the off-peak rate is just under 3 cents. Well, if you've got an air-to-water heat pump that has a COP of 2, and I've talked to the utilities about this, well, with the COP of 2 running that off-peak, how much are you actually paying for that electricity? You're paying literally 2 pennies for electricity to store this. So the energy storage becomes very attractive, and this is why you're seeing utilities in Quebec in particular that have rebates. I believe the rebate is almost $15,000 to put in thermal storage. And as you can imagine, a thermal battery like the one to the left of me, I believe it's going to be somewhere in like the $4,000 to $6,000 range. I don't know, but that's significant. Like these small residential units, it can have a big impact moving forward. This one we kind of talked about already, so I'm going to move on. Integration. I want to talk a little bit about integration and how we sort of integrate that into the system. So as we sort of look at how are we going to do this, the number one thing that we need to make sure is that you pick the right PCM battery for the application. So for example, off to my left here, we were talking earlier, we have a air-to-water heat pump. So that PCM battery is designed to phase change at 58 degrees C because that's the capabilities of that phase change battery. If I'm going to put it on a boiler, I could do a different unit. I could do like a P60 or something higher than that. If I was going to do it in a water-to-water application, I'd probably want to do a 43 because those units are really ideally suited for 110 degrees. And then you also have to figure out how are you going to integrate that battery into the system. Are you using that battery from the standpoint of you want to store the energy for later, or are you using that battery from the standpoint of you potentially want to use it as a dual source heat pump application? So again, I'm going to move just so you can see what I'm talking about. If I go over here, this is a 5-ton air-to-water. Hopefully you can see it okay. And this is a 4-ton PCM battery. Well, I actually have 9 tons of capacity in our lab that I could use for heating. Now, obviously, that extra 4 tons is not there all the time, but how many times do I actually need that? You know, probably 85% of the year, my heat pump is big enough. The few times it's not, you could rely on a PCM battery as your backup heat. And that backup heat could come from waste energy in the building, solar PV, solar thermal, off peak, like literally the sky is the limit. You know, there's limitless opportunities. And those of you on this call, I'm sure have got way better ideas than mine that are coming to mind as you sort of look at this. So it's got a lot of opportunities for us to adopt this technology and really try to utilize it. So load shifting is quite interesting. This is just a better picture so you can see our setup right here. Hopefully you were able to capture it on the camera regardless. But the ability for us to store BTUs in a very small footprint and be able to use that is quite significant. Now, one of the applications that's very popular in Europe that I want to talk about is that for domestic hot water use. So obviously we all know that, you know, hot water tanks, they do suffer from standby heat losses. I'm not going to try to pretend that it's a catastrophe or it's some big deal that, you know, it's the end of the world. We have to put PCM batteries in. Like switching from a gas tank to a PCM battery because of standby losses, nobody's going to do that. But the reality is that there's more that goes into this. And more specifically is it stops the short cycling of whatever you put on it. It doesn't matter whether it's an air to water, a boiler, whatever we're comparing to, when you put a PCM battery on it, it's going to reduce the short cycling. You don't have to take my word for it. I'm going to share some pictures from an NY CERTA study that was done. And there's lots of studies out there you guys can go find on your own. And if you find some good ones, please send them to me. But when you do a PCM battery, it's going to stop the frequent short bursts. And I'm sure you guys have seen that where you go out. I'm sure there's a lot of boiler experts on this call where you go out, you go to a job and the complaint is that, you know, we're having to service this boiler all the time. We're losing igniters and our gas bills are atrocious. And you get out there and it's the indirect, right? Like the 10K is not installed right or the aquastat set up wrong, whatever the case may be. In some cases, nothing's set up wrong. It's just you've got these small trickle loads and the boiler's coming on, off, and it causes a problem for you. So the PCM solution is pretty obvious. We're going to store that energy, but because that PCM battery is storing sensible and latent energy, it's an even temperature. And as we draw it down, it stays the same temperature, right? So if we charge that battery to 58 degrees C, roughly 140 degrees Fahrenheit, that's the temperature we're using until we draw that battery down. It's not like a stratified tank, which is quite unique. And obviously, as we talked earlier, the fact that we can store that heat for when we need it, we don't have the standby losses. So for example, if I charge it up and if I'm not home for 2 days, it doesn't matter. The heat's still there for me when I need it. So when we look at the benefits of what that could mean, it means obviously a reduced gas consumption, which is a lower utility bill. And in some cases, it can be quite staggering. I, in my own house, have an air to water heat pump and I have a gradient sink furnace that takes care of my domestic. And I may have to do this test, right? Because I'm very curious. I've got about 6 studies I'm going to share with you guys where they talk about the reduced gas consumption. And of course, if we reduce the gas, it lowers the utility bill. One of the things that I've seen, and I'm sure a lot of you have seen this on this call as well, is people freaking out about gas bills going, my gas bill doubled. And when you actually talk to them about it, because they assume it's the equipment, it's not a consumption issue. The issue with the gas is the carbon tax. And I'm not going to talk anymore about carbon tax, but it's the carbon tax, the delivery charges, it's not just the gas. In a lot of cases, the consumption is the same. The other thing that's really neat about this is if we burn less fuel, we have a smaller carbon footprint. And I think we can all agree that we would like to reduce our carbon footprint. Everybody, I think, would like to reduce their carbon footprint in a way that makes sense for everybody. If you haven't heard my peanut butter solution, reach out after this webinar. I'll tell you my peanut butter solution. I think it's hilarious. The other thing that's really cool about obviously using this for domestic hot waters, we talked about this earlier, is solar thermal. Solar thermal from a domestic hot water standpoint, I looked at it for my own home. When I did the math on it, I couldn't make it work. With a PCM battery, I'm changing my opinion on that. My ability to store the domestic hot water for when I need it, and the fact that I can store the equivalent of 300 gallons in a small little filing cabinet, that's huge. We could see a big adoption of solar thermal. We could even see manufacturers integrating PCM technology into their solar thermal systems, similar to how manufacturers in the United States are integrating PCM into ceiling tiles, and they're using that for heating through the ceiling tiles. That blew my mind. I look forward to hopefully sharing something on that in the future. And then, of course, we talked about this earlier when I talked about boiler maintenance in the scenario I gave you. It's going to increase the equipment lifespan if we can stop it from running so much. And it's really important, and it's exciting what it can do from that standpoint. So the QR code on the right will take you to a more detailed write-up about this. This was a really cool one. It was not on my radar. What happened here was NY CERTA did a project where they installed a PCM battery on a Wheel McLean boiler, and they were able to reduce the gas consumption and the utility bills by 50%. And that's no joke. So basically what had happened is they'd gone in, they had an existing gas water heater, they had what they deemed to be high gas consumption, and obviously standby heat losses happen on everything. We're not blaming the indirect here. But at the end of the day, the homeowners were looking for a better solution, and NY Serta was involved in this project. And so what they ended up doing was they took out the traditional indirect. It's referred to as a gas hot water heater in the study, but I believe it's an indirect. You'll see in the photos we look at here. They put in a PCM battery. And what ended up happening is, as I say, they significantly reduced the runtime of that boiler. And in this case, it was done with a product called Thermino. So the homeowners achieved a 50% reduction in gas. Now, when you see something like that, you want to see the gas bill, you want to see the data. I have some of that here, but the QR code will help you. You scan the QR code, it'll have more stuff. It has a link to the original study. It has my own spin on it as well, but good opportunity to sort of read up more on this study. And there's many more studies around that. So they found a few things. They found the gas reduction. They saw the utility bills lowered. They saw an improvement in boiler efficiency, which we're also going to talk about, and an overall decrease in energy costs and carbon footprint. So that's pretty exciting considering, again, it's just a box filled with phase change material, a heat exchanger, and there's no moving parts. We can go and do this, and we can achieve this very quickly. So again, earlier NY Serta was referring to it as a water heater. You can see from the illustrations, and these are their illustrations, not mine. You can see on the left-hand side of the gas boiler with the indirect, and then going to the domestic hot water in the house. Well, a couple of things come to play in that. And so when we look at how did we make the boiler more efficient, well, right off the bat, what happened was this Thermino battery they used in this application, it would actually charge at about 140 degrees. So what they were doing is they would charge the battery at 149 degrees, store the sensible and latent energy, whereas before the battery was running at 160 degrees to charge the indirect to provide enough usable heat to the space. So not only did they prevent the boiler from running so much, shockingly, they were also able to make the boiler more efficient. And again, this was not on my radar in the least. I had no time thought, hey, let's put a PCM battery on a gas appliance. But again, part of the fun of this job is we're all nerds, a lot of us, and we like to read too much and talk to people. This one just fell into my inbox, and I was like, this is pretty cool. Because the reality is, how many boilers out there could we go and put a PCM battery on right now and potentially reduce their gas? I'm not going to say up to 50%, which is what happened in this scenario. There's probably something more to the story. But our ability to go in, take out an indirect, put in a PCM battery, reduce their carbon footprint, give them better and more domestic hot water for less money from a fuel efficiency standpoint, like that's a win-win. So as we look at that, again, I've got this here. We've actually already talked about the slide, but basically it went from 170 degree water to 149 degree water. Everything else in the variable stayed the same. This chart is actually showing what was happening. So you can see on the left-hand side, this is the hot water temperature. So on the left-hand side, you can see this is the graph data where it was feeding the indirect. So it was 160 degrees Fahrenheit. And on the right-hand side, you can see that's 140 degrees Fahrenheit. The other thing that you can see in the baseline tank compared to the PCM battery is you'll notice that there is actually a difference in runtime as well. You can see that just from the breaks in the green. That's not what this graph is intended to show, but you can see that there. If we go on to the next graph, we can also see from a domestic hot water standpoint that we were actually able to deliver more water. They were able to deliver more water with the unit running less because the standby losses were insignificant compared to the indirect. And so what they're able to do is at a lower water temperature with lower boiler running time, deliver actually more water than they had before, and the boiler was cycling less, running more efficiently, etc. So it's pretty cool from that standpoint. When we talk about the water consumption standpoint, you can see from the baseline tank, the energy consumption that goes with the water consumption, there is an absolutely massive difference we're seeing here. So the energy required to heat a liter of water reduced by over 50%. And again, not my idea, nothing to do with this. This blew my mind when I saw this. Like, I think this is a really cool opportunity that a lot of people on this can jump on. The other thing is you'll notice my note about the Legionella. And the reason the Legionella is not an issue, again, I'm just going to cut over here, is inside of this PCM material is just a small heat exchanger. So the total volume stored in there is basically nothing. It works like a reverse indirect going from the 50 to 140 as soon as you flow through that unit. Now, If we look at a hydronic heat pump application, obviously you guys have the advantage. I joined from the live fire lab, so I can actually show a few cool things behind me. But I have some pictures from projects in Europe that you can look at. So in this case, what they've done is they've used air to water. And so there was a project in the Berkshire Housing Association where they were actually able to go in and provide significant energy savings for that application. So they're looking at a 59% reduction in carbon emissions, and more importantly, an even more significant drop in gas consumption and bills. One of the things that's really important to me when we talk about heat pumps and as we push for heat pumps and say we need to get off gas, it comes back to my peanut butter solution. It's all fine and good to tell people that they can't use gas, but they need to be able to afford the solution. And that doesn't change the fact that if you can't afford a PCM battery, it's not a solution. Well, if I can't afford my new electrical bill, it's not a solution. So anything that we can do to reduce month-to-month operating costs makes sense. If that's a high-performance indirect that can drop my energy consumption by 50% and also drops my carbon footprint, great. I don't mind paying a little bit more upfront to save each and every month. And that's sort of the thing we need to keep in mind, I feel, as we design systems for consumers, is I think that most of us take my attitude of whatever I design for you, I'd want to have in my own house. And so some of the nice things with the new technology with air-to-water heat pumps and PCM batteries, it gives us the ability to do things that we can't do with an air-to-air heat pump. The air-to-water heat pump, the fact that we can store sensible and latent energy, make it available for later, for when we need it, that is really, really cool. And it gives everybody on this call an opportunity that the air side doesn't have. And as I said earlier, although boilers were not on my radar, those of you that are in areas where, you know, gas is extremely dominant and gas is preferred, again, I'm not going to get into a discussion about carbon, you have an opportunity to go into those applications, go, I can keep this gas boiler and I can reduce your gas consumption by 50% and your carbon production by 30 to 40%. Like that is a win. I honestly wish some politicians were on this so we could talk to them and share ideas with them of like, hey, how do we provide some solutions here? So obviously we sort of talked about this earlier about the time shifting, the opportunities there. These are 4 case studies for 4 different projects of varying sizes. I'm going to start with the one on the left and talk a little bit. I'm not going to go through all of them. I just want to touch on some of the things. So what happened here was energy meters were installed. These were not my projects, but energy meters were installed. They collected data to do some comparisons on savings on heating and hot water. So on the house on the left-hand side, which is case A, they had a 2-bedroom house. It had 2 working occupants that were in the house. They deemed themselves to be heavy hot water users. I mean, they had 2 deep baths. That's probably pretty good heavy hot water users. Their energy savings was 8,400 kilowatts. Their bill savings were 56%. Their CO2 savings were 29.1%. What did they do? They put a PCM battery. That's pretty game changing. That's a pretty simple solution for it. Case B was the same. So case B was 1 more bedroom, so 3 bedrooms, same number of occupants. Their energy savings were 40%, bill savings were 45%. Why is it doing this? It's not rocket science. We're storing sensible and latent energy. The energy is available when we need it. That's basically it. Like the opportunities with this technology. And again, it's a phase change media that in a nutshell is salt. Now, somebody could be on this from a university going, it's much more elaborate than that. It definitely is. But in a nutshell, it's salt. You get into larger applications. We're going to talk about case D right now, where they had a 5-bedroom house, much larger home with some parents and teenagers. Sounds like my house. They saw energy savings of 28,000 kilowatts, bill savings of 50%. Like, it's significant. But the thing that's exciting to me is the CO2 comment, right? All of these studies that you see in front of you, they've reduced the CO2 footprint. And what I like about it is that nobody on this call is faced with going into a home and going, I'd love to do this for you, but we got to upgrade your electrical. I'd love to do this for you, but you know, you've got an old system that I can't upgrade. You won't be comfortable, you won't be happy, or it's going to cost us $100,000 to do it. This is a tangible solution in PCM technology that we can adopt and utilize right now. I talked about this earlier, the off-grid domestic hot water project that I was telling you about. So the photo on the left shows the battery. In the middle is the PV. So basically they had a small amount of solar PV that was installed on the roof. I believe it was 5 kilowatts. On the right-hand side, they had started to show off some of the data to me. I believe I have access to all that data. So if you guys are on this, you're like, hey, share more of that data, reach out to me. I will gladly share that data with you so you can have a look at it. So as we sort of recap a few of the points and we talk about the benefits of a PCM battery, we talked about high energy storage density. So we can store a lot of BTUs in a very small footprint. reduced energy costs. They have a very long lifespan. They're not a new technology. They've been around a very long time, just like boiler technology has been around a long time. And the thing that's really cool is the ability to integrate into renewable systems. If you have a water to water, if you have an air to water, if you have a boiler, solar PV, solar thermal, there are so many options for this technology. It's very cool what you can do with it. Now, obviously, are there some challenges? Yes. It is a new technology to North America. So you do have to be cognizant of the cost of the product. If you can buy, I'm not a salesperson, I don't know pricing, but if you could buy an indirect, let's say for $1,000, the PCM battery might be double, right? But what does the PCM battery do for you? Well, we've got a lot of studies that show the PCM battery is going to reduce your utility bill by half. Okay, what does that mean to you? So if you're in Ontario, that could be significant savings that pays for that battery in the long term. It also provides you with much more hot water. It ensures that your equipment is going to last longer because it's not running as long as it would be. So you have to look at the cost, but don't look at the cost of just the PCM battery. Look at it as a whole system and what goes into that system and what is the potential over the next year, 2 years, 3 years, whatever the case may be. Now, obviously, as PCM batteries get more and more adopted, as the government starts to roll out more rebates and incentives for people to do thermal storage, the cost will come down. It's the chicken and the egg. The more air to water heat pumps we put in, the lower the cost, at least in principle. PCM batteries will be the same. We'll see more manufacturers, which is exciting. And the reality is the people that are working on this technology, the PhDs, the scientists, I love talking to them, like what they have planned and what's coming. We're just starting to scratch the surface. In Europe, they're light years ahead of us. It'll be exciting to see what do we have a year from now. Maybe when we all connect at the CMPX, we can talk about it, or at the AHR show or one of the HRAI or CIPH events and see what's going on. The other thing to be aware of is the thermal conductivity. Some PCMs are not very efficient at heat transfer. So what I mean by that is that you got to pay attention to chemistry. I'm not a chemist. I'm not a PhD. That was really shocking, I'm sure. But you do have to be careful of what is the product, where is it coming from, what case studies are out there, what sort of testing has been done. And in some cases, you just got to do what I did, just buy one and play with it. And that could be really exciting. My last bullet point I already talked about. There's a lot of continued research happening. There are so many cool companies in BC and Toronto that are working on different ways to use this technology, and I appreciate them reaching out and chatting with me. And if you're working on something cool, reach out. Let's compare notes and see what we can do. And as utilities start to adopt this technology, I really think it's going to be good. And what I mean by that is I don't see utilities installing the product. I see utilities looking at this is an easy way for us to do some load shifting, some load shedding. Let's start putting out some incentives to get people to start using thermal storage. And who knows, maybe 5 years from now, we'll see, 1 in 5 homes will have a thermal storage battery installed in them. So as I look at some of my conclusion, my key takeaways, and then I'll sort of throw it out for any questions or comments about what we've talked about today. Phase change thermal batteries, they just offer a really unique form of energy storage. It's really cool. As I said at the very beginning of this presentation, it's been around since about 1915. It was originally used in rocket design. Again, I'm not talking about the phase change batteries we have today, but what was really interesting to me is I thought this was tip of the spear technology. It definitely is. It's evolved a lot over the last few years, but the reality is that this technology has been around a long time. It has a lot of advantages, not least of which is high density. So high density in energy, its longevity, and the biggest thing is the safety factor of it. The ones that I've looked at are all a salt-based. Again, it's not actual salt in the sense of it. I just think it's an easy way to analogize it. That if it leaks out, it's not going to hurt anything. It's not going to hurt anybody. But again, always defer to the manufacturer's guidelines. And the thing that's really excited me is applications of this. There really is. Every time I talk about a PCM battery, whether I'm at a trade show or just in my office or on a phone call, it really excites me, the opportunities that people dream up, whether it's residential, commercial, or industrial. And I think there's a lot of opportunities to come. And in the future, I think we can expect some really cool advancements, specifically in cost effectiveness. As more and more people adopt this technology and move away from other storage systems, there's going to be wider adoption and there's going to be more options. The last thing I would just sort of like to close with is that I'm by no means saying that PCM technology is the be-all, end-all. There's still going to be a place for other types of storage. You're seeing a lot of brick storage. You see sand storage. I'm talking about phase change thermal storage because I like the fact it's compact. I can put it in my house. I can put it in your house. It's very easy to do. It's very low maintenance. But there's a lot of other thermal storage options that are out there. And the adoption of this technology is very exciting, and we don't really know yet what the future is going to hold. So on that note, I have my QR code again. If you'd like to connect with me, take your camera app out, just hold it over, a little link will come up, click on it. That's me. I would definitely love to hear from you. Otherwise, I thank you for attending, and I believe I ended with pretty good timing. We got a few minutes to take some questions if there are any. We'll see if one of the ladies from CIPH has questions. I'll sip my coffee. And if you have questions, I think you can put them in the Q&A. Okay, so I got a question. It's from Matthew Beck. And I don't know how to unmute you, Matthew, or I would, and we would just have a conversation about it. So 2 tanks, simultaneous heating and cooling. So Matthew, great question. Yes. If I was going to do heating and cooling, I would end up with 2 PCM batteries. One would be using a 58-degree material, and the other one would be using a much lower temperature that's designed for storing chilled water. I haven't had the opportunity to play with one of the chilled storage units yet. But I'm hoping to get my hands on one in the near future and be able to poke around with it. But when you're looking at doing heating, cooling, regardless of the application, what you need to be aware of is what is the temperature you're producing. So if you've got a situation where you go, okay, I've got a unit that in cooling produces 45 degrees Fahrenheit, you need to make sure your phase change battery is able to phase change at 45 degrees, give or take, and store that energy. Adrian says, great presentation. Thank you, Adrian. I appreciate that. So let's see here. Could you pipe them together for higher ultimate COP? Yes, you absolutely could. So there is a project that's being worked on right now, not my project. And what they're doing is they're taking 2 thermal batteries. One is 58 degrees and one is 43 degrees. And so what they're doing is they're putting these 2 batteries together to maximize the overall COP of the heat pump by having 2 different temperature PCM batteries. I was hoping to have photos for this presentation, but unfortunately, sometimes a lot of things get shared with me with the caveat of, Michael, you can look at this, but you can't share it yet. But anybody who sends stuff to me has to know that I want to share it. Those of you who know me and have seen any of the things I do, I like to share everything I work on. I think it's fun. And in sharing, I find that a lot of people, like people on this webinar, are willing to share back. And I think it's important that we try to help each other. It's a small industry. We should do what we can for each other. Mason says, do you know if the manufacturers are providing piping diagrams for retrofit or upgrades to existing systems? Okay, so I'm going to scroll over here and show you mine really quickly. So it's pretty simple. Basically, all you need to be able to do is you have your charging ports and you have your discharge ports. The number one thing that I will point out to you, and you saw it probably in that photo, is typically they have a flat heat exchanger inside of them, sort of like a hydronic coil. In fact, it literally is a hydronic coil. The pressure drop's really high. So I've only ever seen one that I got asked to look at recently. Again, not my job. I had nothing to do with it. That didn't work so good. And the reason it didn't work so good is they had a tiny residential hydronic circulator on it. That's not going to cut it. So if you look at mine, you might not be able to see it, but let me try and show you. On mine right here, what I've got is I've got a beefy Takeo 0013 on my PCM battery because there's a fair amount of pressure drop inside of it. The other thing I'm doing with my PCM battery, you don't actually need a 0013. Let me just show you why. Is over here where you can't see, I have a 5-ton air handler that's dumping the battery. So that Measurement Canada meter, we charge it. This little dongle that's double-sided tape isn't working so good, guys, but the rest of the lab's pretty cool. It read-writes all the data off this unit. So what I'm doing is I'm seeing how many BTUs, how much flow, what's the compressor RPM that's feeding into this battery, and then I'm using the Measurement Canada certified meter that I have from Belimo to actually measure the discharge of the battery. So pretty long, convoluted answer, Mason, but the reality is the piping is super easy. If you send me an email with like, hey, how would you pipe this? It would take me 2 seconds to do you a drawing, and it would look pretty good. I won't use crayons. I'll do it on the computer. Bill says, ballpark wholesale cost. That is a loaded question, Bill. Not a sales guy. I would expect it would probably go out to the trade for somewhere in like the $5,000 range. If you send me an email afterwards, I can probably connect you with somebody who's in your area. Again, I don't want this to turn into a sales pitch for anything, but I understand why you're asking. How do we offer technology if we don't know what it costs? But I guess it's probably in the ballpark of like a high end indirect. But again, it has its advantages versus a high high performance indirect. It also has some disadvantages, right? Like a PCM battery, you have to pick it for a specific temperature. You can exceed that temperature. So if you pick one that's designed for 140, you can feed 170-degree water into it, but you can't feed 130 into it, right? If you put 130-degree water into a PCM battery, it's not going to phase change. And indirect's a little bit similar in that sense, but indirect's more forgiving. You're still going to have some hot water there because you got a lot of water storing it. The advantage, again, to the PCM battery is its ability to store sensible and latent energy, which we can't do with water-based storage. I believe I have answered all of the questions.